In this chapter, we study normal modes. First, we consider doubly coupled harmonic oscillator, and normal mode should be. We should study normal mode to consider system of harmonic oscillators. That means connected oscillators of n degrees of freedom. Here, the degrees of freedom is the number of massive particles in a system. As shown in this figure, this doubly coupled harmonic oscillator consists of two massive particles and three springs. At both ends are fixed, and in the middle there's a connection. The two masses are connected each other. And to simplify the analysis, we consider the case that these two springs are identical to each other, and the other spring is giving some sort of weak coupling between them. Without this, the spring in the middle, the two massive particles oscillate completely independently. However, because of the spring in the middle with the spring constant kappa, the oscillation of the system are coupled. The resultant equation is a coupled differential equation. That means we cannot solve x1 and x2 independently. However, if we reorganize this linear equation, at some point we find that the two equations are decoupled, and decoupled means we can introduce the two independent coordinates that can express both x1 and x2, and they are expressed as a single harmonic oscillator separately. First, let us construct the equation of motion. The equation of motion for a single massive particle attached to a spring of a spring constant k. The equation of motion can be written in the F equals ma style, and the differential equation involves a single variable x that depends on that is function of time. And we know how to solve this problem, and there exist two linearly independent solutions, that is cosine sine of angular frequency omega 0, that is square root of k over m, and the solution is a linear combination of e to the I omega 0 t and e to the minus I omega 0 t. Or we can express these solutions in terms of cosine omega 0 t and sine omega 0 t. So this single variable second linear differential equation can be solved in quite an easy way, and we know how to do that. In case we have two massive particles attached to springs separately, and then they are connected by a spring in the middle with the spring constant kappa. Suppose that these two particles are at the equilibrium point, so that these three springs are relaxed and they do not contribute any force at all. And let us keep this x2 at rest and just shift the first massive particle to the right by the displacement x1. The restoring force appears in the left spring and right spring both. And because the spring constant is k for the left one and kappa for the right one, the force applied to this object is minus kx1 and minus kappa x1. Okay. So we have additive contribution of this k and kappa for the displacement x1. But what about the case when this x2 is also shifted? The first, the origin has been shifted by x2 and the left hand is fixed. The contribution of the left spring on this object is still minus kx1 because the shift from the equilibrium position is just x1. However, the force applied to this object by the spring in the middle is different from the original one because the reference point has been shifted. The effect of this shift can be formulated in such a way that x1 subtracted by x2, because the reference point used to be the 0, but it is replaced with x2. The translation by x2 can be formulated as x1 minus x2. That is the change in the spring displacement. The displacement of the spring from the equilibrium position can be made in such a way. Therefore, the equation of motion for the left massive particle is mass times acceleration, and the force on the left spring from the left spring is minus kx1, and the force coming from the right spring is minus kappa x1 minus x2. In a similar manner, we can compute the force applied to the right object to be, we just exchange 1 and 2. That means minus, this spring gives minus kx2, and the spring in the middle applies some force. That force is kappa x2 minus x1. This equation can be simplified by making use of the matrix wait a second. And these two, left side is expressed in terms of a second derivative of the column vector. Now we have introduced a capital X to be a column vector consisting of two coordinates, x1 and x2. This is second order derivative, and we have mass, but mass is applied to the first and second particle because they are identical particles. So we have the same mass for x1 and x2. So the mass matrix of this system is just m times identity matrix. If we reorganize this expression to the left hand side and pull out the factor of column vector x, then the coefficient of x1 becomes a k plus kappa. Coefficient of x2 is minus k because it is plus, and if it's moved to the left, it is a minus k kappa. The same is true for x2 equation, but the coefficients are exchanged for x1 and x2. So, resultant equation of motion is this one. For simplicity, we re-express this vector k plus kappa over m to be a, and kappa over m to be b. And the equation of motion becomes in a compact form, double time derivative of column vector x plus omega square x equals 0, where omega square is this one. We find that this matrix is symmetric, and this matrix is real and symmetric. So then it's omega square star is omega square transpose is omega square, thus omega square dagger is omega square. That means it is Hermitian. We recall that any Hermitian matrix can be diagonalizable. As a result, if we can diagonalize this matrix, then the equation, this coupled equation, becomes completely decoupled. Now, let us diagonalize the matrix to find the decoupled equation. The decoupled equation can be expressed in terms of normal modes. This is the equation of motion that we want to solve, and omega squared was k plus kappa over m for the diagonal elements, and minus kappa over m for the off diagonal elements. This is real and symmetric, and to simplify this expression, we have substituted this and this coefficients in terms of a and b. As I already told you, the matrix is real and symmetric, therefore it is Hermitian. And in the matrix chapter, we learned that Hermitian matrices can always be diagonalizable. And in order to diagonalize that matrix, we have to find the eigenvalue problem. And the eigenvalue problem can be constructed in such a way: omega square matrix multiplied by an eigenvector becomes proportional to the eigenvector, and the proportional constant is omega I squared. That is, because it is Hermitian, that number is a real number, and there must exist n such number. But we have n by n matrix, n equals 2. We need to have 2 real eigenvalues. Sure, it is possible to have degenerate eigenstates. So in that case, even in that case, there exist 2 linearly independent eigenvectors. Those eigenvectors are linearly independent. However, it is also perpendicular to each other, absolutely perpendicular to each other. So once we find 2 orthogonal eigenvectors, we can always construct normalized eigenvectors. Normalized eigenvector is defined to be, once you find the eigenvector, the square the eigenvector and take the square root, divide this vector by this vector. So then we are prepared to have the orthonormal basis eigenvector. Therefore, if the scalar product can be made to find the Kronecker delta. The matrix lambda that diagonalizes this matrix omega squared can be found by constructing a matrix whose rows are the Hermitian conjugate of every eigenvectors. We can list these eigenvectors. This is row vectors. We can check it diagonalizes the system. For example, lambda multiplied by psi 1, because of this orthogonality relation, if I multiply the eigenvector psi 1 to the lambda, we have identity, this unity for the first one, and second one is orthogonal, so 0. If I multiply this psi 2, the second eigenvector, then the first element vanishes and second element survives. And combining these two pieces, for example, we have lambda and a matrix consisting of two column vectors as eigenvectors, then it becomes identity. Right? Therefore, there is a lambda. If there is a lambda, such it can be, because we can always construct the eigenvectors and normalize eigenvectors. We can always find the matrix, and then matrix Hermitian conjugate is this one, and matrix multiplied by its Hermitian conjugate becomes always identity. That means this lambda is a unitary matrix. As a special case, if lambda is real, lambda is orthogonal. Now let us solve the equation of motion. Equation of motion is not a form of this eigenvalue problem. But once you know the eigenvalue, eigenvector and eigenvalue for this matrix, we can think about the possibility of solving the differential equation. Let us first try the separation of variable. That means the time dependence of this x is completely factored out in this manner. It has a single frequency, a single angular frequency. Sure, it is a system of a real variable. However, even though we are working on a real variable case, the differential equation can be solved in a very simple way by introducing a complex variable. For example, we can substitute time dependence at e to the I omega t, e to the minus I omega t, e to the lambda t, something like that. Anyway, let us first assume that the time dependence appears as a separate way multiplied to the eigenvector. It is possible, it is reasonable way of introduction of this trial solution, because as we know, the eigenvectors are independent of time. So if the eigenvectors are independent of time, what happens to the time dependence? That should be factored out in an arbitrary way, but among them, this is the simplest trial solution. So it is not an ad hoc problem, but ad hoc treatment, but it is a consistent way of solving this equation. This kind of separation of variable appears in many cases for the partial differential equations. Now we were able to find the transformation matrix that diagonalized lambda, and the resultant diagonalized form of omega squared, that is omega d diagonal, is just the eigenvalues. Diagonal elements are eigenvalues, and all the off-diagonal elements are vanishing. We just have introduced the trial function, but we have the equation of motion. What was that? That is x double dot plus omega squared x equals 0. right? We substitute this trial solution into this linear differential equation, right? Then what happens? The second derivative gives minus omega squared. If I substitute in here, what we find is omega squared minus identity psi e to t minus I omega t is factored out. So because it is non-zero, we have this eigenvalue problem. That eigenvalue problem can be solved only if this matrix is not invertible. If the matrix is invertible, we can multiply this inverse matrix of this to find that psi is completely exactly zero. That we call that kind of answer to be trivial solution. But in physics, we do not consider, and we are not interested in the trivial solution that is exactly zero, but that does not describe any oscillating system. So it's just completely at rest, the system. So the non-vanishing eigenvectors are obtained only if this matrix is not invertible. That means the eigenvalue of this matrix must vanish. The fundamental theorem of algebra tells us that there are complex solutions. For number of rows, we have determinant has a quadratic form. 2 by 2 is quadratic form for omega squared, and there must be 2 omega squared. In case if they are the same, we double root can be considered as multiplicities. So with multiplicities, there should be 2 eigenvalues. But we remember that because omega squared is the Hermitian matrix, those eigenvalues are all real, and corresponding eigenvectors are all orthogonal. The determinant of this is a minus omega squared minus b squared. So the circular equation states that omega a minus omega squared is either plus b or minus b. Substituting this a minus omega into the linear equation, we find these two equations. Wait a second, just to look into this solution to learn how to obtain the eigenvector of the system and how to normalize those eigenvectors as a unit normalization. So in this case, we substitute a minus omega squared with b. Then linear equation has this style: b minus b minus bb. Suppose that we assume the eigenvector has a x, y, and y components, and the solution of non-vanishing this eigenvector can be determined as 1, 1. Because they have different sign. In the case of minus b, we have the same sign and same magnitude, That means x and y are the same in magnitude and opposite in sign. The corresponding eigenvalue for the first vector, 1, 1, is omega squared k over m. The second one is k plus 2 kappa over m. And the normalization can be corrected. It's with the union normalization. So psi 1 and psi 2 are obtained in such a way. We can construct a rotation, the transformation matrix to diagonalize this matrix. That is psi 1 dagger and psi 2 dagger. Its Hermitian conjugate should be psi 1 and psi 2. We can diagonalize this matrix by multiplying these two matrices. And the result should be the diagonal elements, the diagonal matrix whose diagonal elements are omega 1 squared and omega 2 squared. We substitute these two values into the here to find out the final result. Now we find that psi has unique frequency. Psi 1 has this frequency omega 1 and psi 2 has omega 2. So if I consider this psi as we have two non-vanishing components for x1 and x2, then means the combination of x1 and x2, if, for example, x1 plus x2 or x1 minus x2, that kind of contribution has a single frequency. Now, at the original, the original equation, coupled equation was in the form, and the matrix was real and symmetric. Thus, it is a Hermitian, and it was diagonalizable. We have found that eigenvectors. So eigenvectors can be used to find out the transformation matrices. Now we introduce the normal modes. Normal modes is if I multiply lambda to this matrix, it becomes this one. And the equation becomes diagonalized. X double dot plus omega squared x equals 0. We multiply lambda because it is a unitary. So we call eta to be lambda x, right? Then eta double dot plus equals 0. We know that let omega d squared is omega 1 squared and omega 2 squared. Therefore, if eta is eta 1, eta 2, this shows that because it's diagonal, in this form, because it is diagonal, the equation is completely decoupled. The first element and second element are independent equations. The first element is just eta 1 double dot plus k over m. There's omega 1 squared, eta 1, and the eta 2 double time derivative plus k plus 2 kappa over m, eta 2 equals 0. That means these two equations are completely decoupled. And their eigenvectors are orthogonal. That's the reason why we call this as the normal coordinates. Normal coordinates. Sides are orthogonal, so its coefficient is called normal coordinates. Now, the equation of motion for these normal coordinates can be solved a trivial way because it's a simple harmonic oscillator. By making use of the simple harmonic oscillator solutions, we can reconstruct the final result for the x1 and x2 that can be made if I multiply the lambda dagger, it becomes x. So by diagonalizing the matrix omega d squared, omega squared into omega d squared, the equation of motion for the x1 x2 are completely decoupled once we express the equation in terms of the normal coordinates. So by solving the normal coordinates, we substitute the solutions and multiply the inverse matrix lambda dagger that lambda was used to diagonalize the matrix. We find out the final result for the x1 and x2. Now, let us consider some specific example. The initial conditions for x1 and x2 are given in here, and velocities are all vanishing at the initial stage. Then what is the solution for x1 and x2? Sure, we can directly solve this problem if we are genius, but we had better to introduce the normal modes and to find out the solution. For example, this is the equation of motion for two normal coordinates, and the solutions are linear combination of cosine and sine, but they have distinct natural frequencies. Now the initial conditions for x1 and x2 are given in here. It is x1 and x2 at t equals 0. The given initial conditions are d0, and initial condition for the velocity of x1 and x2 are both 0. Now we can transform into the normal modes. The initial condition can be obtained. Initial conditions for the normal coordinates can be obtained by multiplying the lambda matrix to the original vector coordinate vectors x1 and x2. So eta 0 can be obtained by multiplying lambda to x0. This value is 1 over square root of 2 d minus d. Because x1 dot and x2, both x1 dot and x2 dot are vanishing, the initial condition for eta 0 dot, eta dot 0 are also vanishing. Sorry. So in here, we can make use of the general solution for the homogeneous equation for eta 1 and eta 2. Eta 1 has a frequency omega 1, that is square root k over m. Eta 2 has a frequency of omega 2, that is square root k plus 2 kappa over m. We first consider the case eta 1. If we substitute t equals 0, we have alpha 1. Right? That is alpha 1. But this condition gives eta 1 has 1 over d over square root 2. What about eta 1 dot 0? Eta 1 dot 0, if I take the derivative and substitute t equals 0, only this contribution survives. That is beta 1 omega 1. But the initial condition gives eta 1, 0, that is vanishing. Therefore, because omega 1 is non-zero, beta 1 must be 0. In a similar manner, we can determine the normal coordinate for the eta 2. The normal coordinate eta 2 is determined as, if we substitute t equals 0, it becomes alpha 2, but the condition is minus d over square root of 2. Eta 2 dot 0 is again beta 2 omega 2 cosine omega 2t. Substitute, we can substitute t equals 0, that is the non-vanishing component, but given condition is 0. Therefore, beta 2 is also vanishing. Substituting these conditions into the general solutions, we find that eta 1 is d over square root of 2 cosine omega 1t, that is d over square root of 2 cosine square root of k over mt. And the other normal coordinate has a different sign and different frequency. And we have indeed different frequencies. Once we obtain the normal coordinates, we can reconstruct the original coordinates that by multiplying the inverse transformation matrix lambda dagger. These eta 1 and eta 2 are given in here. Eta 1 with the amplitude d over square root of 2, eta 1, eta 2 multiplied by this lambda dagger gives the linear combination of two different frequencies. This was the reason why the original equation was a couple, and it was rather complicated the final stage. But this complicated nature can always be separated into two pieces that are completely decoupled, that we call the normal coordinates and normal mode. The method of the normal mode is based on the nature that any Hermitian matrices can be diagonalized, and it has a real and real if the Hermitian matrix is n by n, it has real eigenvalues and all of the eigenvectors are orthogonal. This is the final result that we already obtained here. Now let us consider a small oscillation of system of particles. This is the reason why we study this is we would like to extend this method of normal coordinates to n oscillators. Once we extend this method to n oscillators, you'd like to extend this method to the case n goes to infinity. We shall find that this extension from the coupled oscillator to n goes to countable infinity case to be the Hilbert space. And Hilbert space is closely related to the quantum mechanical wave functions that are all orthogonal, and that can be extended to the case in which the wave function expressed in terms of the complex numbers. That's the reason why even though we do not need to introduce, we always construct a formalism that is consistent with the complex numbers. First, let us consider a kinetic energy of a system of particles consistent with particles. And particles moving around in the three-dimensional space has a velocity of x component, y component, and z component. We first assume that the mass of each particle is distinct, so we put a subscript k for the kth particle. And to simplify our analysis, as usual, we consider the case that the coordinates does not have any explicit time dependence. So velocity of a particle. Now let us express this in terms of generalized coordinates. If there are n particles, small n particles, and there are 3 coordinates for x, y, z directions, then we can introduce the 3n. Capital N becomes 3 times the small n. Number of particles is small n, and number of independent coordinates are 3 times the small n. That we call the capital N. So we need to introduce the 3n, 3 small n, there's capital N, generalized coordinates. The expression for the velocity squared is needed to express the kinetic energy. You can expect that we would like to construct the Lagrangian of the system. Then we have qi dot and qj dot, and we need to multiply these coefficients, the partial differentials, and multiply the mass to find out the kinetic energy of the system of particles. There is a complicated object that has a mass of each particle and relationship among the coordinates, from the Cartesian coordinates to the generalized coordinates given in here, and that is called, this is the exact expression for mass matrix. There is a mass matrix, and we multiply qi dot and qj dot, that is a time derivative of generalized coordinates. If we introduce a column vector consisting whose elements are generalized coordinates, this complicated expression becomes very, very complex. That's the q dot dagger, mass matrix, and q dot 1/2. Next, we consider the case that this system makes a small oscillation near the equilibrium position. Equilibrium position means that q double dot equals 0 at a certain point. And we define the coordinates so that its origin is placed at the equilibrium position. And we'd like to consider the mechanics of this oscillating system with a small amplitude. Wait a second. So, in order to construct a Lagrangian, we were able to write down the kinetic energy of the system. Next, we consider the potential energy of the system. Suppose that the potential energy is expressed in terms of n generalized coordinates, but we have a constraint that the coordinates can be used to expand the potential energy. We recall that the system has These are the generalized coordinates written in the column vector, and q dagger is given here. Let us first consider the equation of motion. We need Euler-Lagrange equation. In order to find out the Euler-Lagrange equation, we first need to find out the conjugate momentum. It's a time derivative of conjugate momentum, and conjugate momentum can be found in this. The calculation is given in here. Conjugate momentum is the partial derivative of Lagrangian with respect to the time derivative of generalized coordinate qi. So, because we do not consider the velocity dependent potential, the q dot derivative does not appear for the potential energy contribution. Only the kinetic energy contribution gives that value. The kinetic energy can be differentiated. Now we made use of the mass matrix expression. If I take the derivative, this one gives Kronecker delta A. If I take the derivative of this one gives Kronecker delta B. The final result will be MIB multiplied by QB dot and MAI QA dot. We recall that mass matrix is symmetric on the exchange of two indices. Because they are symmetric, this order is reordered, and now we have dummy index B for the first term and dummy index A for the second term. Dummy index can always be replaced with anything, so these two contributions are the same. Therefore, the conjugate momentum, the canonical momentum conjugate to the coordinate qi should be MIA QA dot. That means in a matrix form, it is compact, expressed in a compact way. So now, if we want to find out the Euler-Lagrange equation, now we know how to write this term. And next one is the force. The generalized force can be obtained. This one is 0. First, we didn't consider the case the mass matrix has a coordinate dependence. If I take the partial derivative with respect to the coordinate, then this is a q dot dependence, so it completely vanishes for the T, kinetic energy, and the contribution coming from the potential energy should be 0 at q equals 0, because we are describing the system from the value from the position at which the equilibrium is made. Therefore, q double dot vanishes at the equilibrium point. Around that equilibrium point, the potential energy can be expanded. So the Taylor series expansion gives in this kind of form. Now we have selected the origin to be the equilibrium point, and this first order contribution of the expansion, Taylor series expansion with respect to Q vanishes because the first order derivative of potential vanishes at that origin, that is the equilibrium point. So the first non-vanishing contribution, sure, this one is non-vanishing, but the potential energy, the constant contribution in the potential energy does not make any physical contribution to the force. So this one is negligible. This one can always be neglected to be 0. So the first non-vanishing contribution of the potential appears in the second order. It's a second order, but it is mixed with Qi and Qj in a complicated form. So we can define a matrix that is called the potential energy tensor, the second order derivative of U around the position of equilibrium. If the oscillation around that equilibrium position has the small amplitude, then this potential energy of the second order is sufficient to describe the system. However, if the amplitude is very large, then the neglected contribution may arise. So this system, this consideration is valid only if the amplitude of the whole oscillation is very small. Now we are ready to express this potential energy in a matrix form. In a matrix form, we can write it in this kind of form. This is the potential energy and this is the Lagrange. Again, we can find out the generalized force by taking the partial derivative with respect to the coordinate in a similar manner as we have done for the mass matrix. We have potential energy tensor appears and derivative gives the first one and second one derivative, and we organize we apply the symmetry of the symmetric matrix A. So the generalized force can be obtained by multiplying A to the coordinate. As a result, Euler-Lagrange equation is expressed in this way, and it is expressed in terms of a matrix equation in a more compact way. Wait a second. Okay. Let us extend this method to the general case. Now we end up with the equation of motion for n-particle system oscillating around the equilibrium position with a small amplitude. And we also have found the Lagrangian is of the form. This was the Lagrangian, and we recall that the mass matrix is symmetric and real. That means a mass matrix is a Hermitian, and potential energy tensor is also a Hermitian. Now we introduce again with the trial solution. In the previous case, this mass matrix was identity multiplied by the mass, but in here we consider the general case mass matrix is a Hermitian. That means there exists non-vanishing contribution for the off-diagonal pieces. Even in that case, we can also introduce a trial solution based on the separation of variables. The spatial dependence, the position dependence of the particle dependence and time dependence can be separated. Sure, at the final stage we will find that the solution for Q is a linear combination of these states. Now, this eigenvector should be independent of time. The eigenvector is composed of eigenvector is a column vector whose coordinates are independent of time. If I substitute this one in here, the second order time derivative of Q is minus omega squared, and because the psi is independent of time, the resultant equation for this becomes this one. That means that we again find out the eigenvalue equation. So let us look at the right side. This is the coordinates for n particles in a system. we introduce a trial solution based on the separation of variables, time dependence, and particle dependence are separated. Second order time derivative is minus omega squared multiplied by the original vector. Substituting this one into equation of motion, we find this. This equation is another eigenvalue problem. In the previous case, we had identity in here, but instead we have Hermitian matrix capital M for the mass matrix. We move this one to the left hand side to find out that A minus omega squared M multiplied by eigenvector should vanish. Again, we are interested in the non-vanishing, that's a non-trivial solution for the eigenvector. So in case this matrix has an inverse, if we can multiply the inverse to the left, then psi becomes trivial solution, is all components are 0. But we are interested in the non-trivial solution. So if there exists a non-trivial solution, then this one must not be invertible. That means determinant of this matrix should vanish. Again, this is a cyclic equation. And fundamental theorem for algebra states that the determinant of this n by n matrix must be a order n, degree n. Therefore, the solution for this eigenvalues are n, where n is given in here. Again, because these two matrices are Hermitian, we shall find that the eigenvalues are all real, and the eigenvectors are all orthogonal. Even though there are some multiplicities, the eigenvectors are all orthogonal. Let us prove those statements. First, let us write down the eigenvalue equation in this way. This is eigenvalue equation for the index I, and we write down another eigenvalue equation as different eigenvalue and different eigenvectors. Sure, it can also be I and j can be the same and may not be the same. So I and j runs from 1 to capital N. That is the number of particles. First equation can be, we take the Hermitian conjugate of the first equation to find that this, and the Hermitian conjugate the first equation multiplied by psi j. So Hermitian conjugate of this one multiplied by psi j. Hermitian conjugate of this one multiplied by psi j. Now the matrix should be written in here. Because lambda is eigenvalue, the complex conjugate appears in here. We remember A is real and symmetry. That means A is Hermitian. And M is also true. This M is Hermitian too. Therefore, this Hermitian conjugate gives the same matrix. Hermitian conjugate gives the same matrix. Hermitian conjugate gives the same matrix. The only difference, and second equation, we multiply psi I dagger to the second equation. If I multiply psi I dagger to the second equation, the left hand side, psi I dagger A psi j. The left hand side of these two equations are identical to each other. The right hand side has a structure I and j. However, they can be vectored. However, I and j with different eigenvalues and One is just eigenvalue, and the other one is it's a complex conjugate. First, let us consider the case I and j are the same. If I and j are the same, the difference of his imaginary part, in proportion to the imaginary part eigenvalue, multiplied by psi dagger m psi I. Suppose that psi I is consists of the n complex numbers in the components. Because M is a symmetric matrix, we can always exchange the indices I and j. That means Mij is a product of two numbers, and actually it is a real number. Mij can be substituted in here, and the psi I can be substituted in here. We find this because the C is a real number, C is Ca, any component, and its complex conjugate should be the same. Therefore, after the calculation, we find that this is a complex number multiplied by as a complex conjugate. That means this absolute value of a complex number. That means it is always positive definite, because these mass matrix, it is impossible to have all of the components of a mass matrix is 0 and all of the components of this psi is 0, because we are not considering the trivial case, but we are considering the non-trivial case, non-trivial solution case. As a result, this one is a positive definite. We can divide this factor out in both the equation. The result is psi I complex conjugate should lambda I complex conjugate equals to the lambda I itself. That means lambda I does not have any imaginary part. That means lambda I is a real number. This is the proof of the real eigenvalue. If I and j are different, now we have this kind of form. If the two eigenvalues are different, then they are orthogonal. It is possible to have the same eigenvalue, but even in that case, we can always find the linearly independent, that is orthogonal element in the basis vector that has not been chosen for the eigenvalues already chosen. Therefore, it is always possible to construct a basis vector by making use of the eigenvectors. Now, we have the normalization condition for the general case in which the mass matrix is symmetric. In comparison with the previous case, we had the identity matrix multiplied by mass, but this is a general real symmetric mass matrix. Even though real symmetric mass matrix exists, we can always normalize to the unity for the eigenvectors. Because of the appearance of this mass matrix, we can put this mass matrix in here to the right side or left side. Once you have Kronecker deltas for the normalization condition, we can always construct a completeness relation. This is the elementary case for the Cartesian unit vectors that spans the Euclidean space. And these identities can be employed to construct a completeness relation for the general mass matrix case. Hermitian conjugate, and this case shows that this is original form, and the mass dependence appears on the right, either on the right and on the left. And further simplification can be made, and this is a cross-check for this formula. We take the trace for this system, and you can find a simple relation for this Kronecker delta. just to review what I have solved. Now, our equation of motion began with this, but we have found that the expression can be solved. This equation can be solved using eigenvector, and the coefficient of the eigenvector has the complete time dependence, and we have introduced e to the minus I omega t style, and this one is a so-called the normal coordinate. And each normal coordinate has a characteristic frequency of the eigenvector, and the system is completely decoupled, and we have n independent oscillators. All right. Now, in summary, let us review what we have done until now. Lagrangian of the system that is oscillating about the equilibrium position at which the potential energy is minimized. That means for each coordinate, for every coordinate, the first order coordinate derivative of the potential energy vanishes at the origin. So we have made a Taylor series expansion for this potential energy, and the constant piece was observed to be zero. The constant contribution to the potential energy is does not contribute to the equation of motion, so neglect the constant piece. And first order expansion vanishes because the first order coordinate derivative of the potential energy vanishes. The first leading non-vanishing contribution to the potential energy was a quadratic form in Q. That means we can expand that potential energy in powers of Q, and the second order piece is written in this form, where this potential energy tensor is the second order derivative of the potential energy with respect to Qi and Qj. That double derivative determines the potential energy tensor, and that potential energy tensor is real and symmetric. We also remember that the mass matrix of the system is real and symmetric. Equation of motion can be obtained by making use of Euler-Lagrange equation, and that equation of motion was like that. We introduced a trial solution that separates the dependence of the particle in the system and the time dependence as a product e to the minus I omega t multiplied by the eigenvector. The double time derivative of that eigenvector is independent of time, so omega squared appears, and double time derivative was replaced with the constant vector that is a characteristic frequency squared minus. Because of that, we were able to solve the eigenvalue equation, and by solving the Decoupled equation, we have found that there are n characteristic frequencies with multiplicities, and the corresponding eigenvectors are all orthogonal, and we have found a useful normalization condition to diagonalize the matrix. Then all of the coordinates can be expanded as a linear combination of eigenvectors, and this is called the normal coordinate. We remember that AQ is a potential energy tensor. We substitute this Q in here, and What's that? We have the eigenvalue equation. We can replace this eigenvalue equation with the frequency squared. And frequency squared and the mass times the eigenvector. Now, this is copied in here. We multiply the Hermitian conjugate of the eigenvector. The normalization condition for the eigenvector was delta Rs for this state. Therefore, this one shows that if we have AQ, if we multiply the eigenvector Hermitian conjugate, we just select the normal coordinate multiplied by the frequency squared. What happens to the case if I multiply the Hermitian conjugate of the eigenvector to MQ? M and Q is expanded in this way. Normal, this is eigenvector and whose components are normal coordinates. And then we multiply the eigenvector Hermitian conjugate. The result is the Kronecker delta. So, if I multiply Hermitian conjugate of the eigenvector to MQ, then final result is the normal coordinate itself. As a result, equation of motion is simplified to be the n independent normal coordinates harmonic oscillators. As this is shown here, all of the n harmonic oscillators for the normal coordinates are completely decoupled. In summary, we have normal coordinates whose elements are like that, just like what we have done in expanding an Euclidean vector as a linear combination of unit Cartesian vectors E1 to En, and we call the coefficients of this to be the coordinates. These x1, x2, these are Cartesian coordinates of Euclidean vector. In a generalized coordinates, we can also express in terms of this Cartesian coordinates of this all generalized coordinates. However, we change the basis from those immediate expression for the basis vector with the eigenvectors. They are more natural, that has a separate natural frequencies. And each basis vector is normalized to be unity with this normalization condition, and all of the generalized coordinate can be expanded as a linear combination of eigenvectors. All of the coefficients, just like x1 to xn for the Cartesian coordinate, are called normal coordinates because they have basis vector, they are all normal. And this, once we obtain the normal coordinates, then the equation of motion is completely decoupled. For example, in the potential energy, we can insert the identity matrix by making use of the completeness relation. We insert this to find that this one is normal coordinates complex conjugate, and this one is normal coordinate multiplied by its frequency square. Therefore, potential energy was expressed in the complicated mixture. They are all separated into n pieces. Each piece has a 1/2 omega squared eta star eta style. And these oscillators are all separated. This can be also understood as a diagonalized matrix, and this is diagonal oscillating omega squared d is all diagonal. So even though there are, it is possible to have non-trivial, non-diagonal pieces, off-diagonal pieces, because omega d is diagonalized. There is no mixture of the any two states. Only a single state contribute. In a similar manner, kinetic energy is also decoupled into single pieces. So this is a matrix form. This is summation over indices.